Fiber optic sensing. Fiber optic sensing uses the physical properties of light as it travels along a fiber to detect changes in temperature, strain, and other parameters. Fiber optic sensing utilizes the fiber as the sensor to create thousands of continuous sensor points along the fiber. This is called distributed fiber optic sensing using a distributed fiber optic sensor. The devices measuring the fiber itself are generally called interrogators. The purpose is to use a standard or specific fiber for measuring the temperature and strain along it using Raman and Brillouin distributed fiber optic sensor techniques. For instance, by using fiber sensing interrogator, one can detect and locate any hot spot along your power cable, detect and locate any excessive strain on your optical cable and react before the break. A fiber optic cable can act as the communication path between a test station and an external sensor, which is known as extrinsic sensing. However, when the fiber itself acts as the fiber optic sensing system, this is known as intrinsic fiber sensing. The benefit of this type of fiber sensing technology is that discrete interfaces between the fiber and external sensors are not required, which reduces complexity and cost. In order to make this possible, external stimulation such as temperature and strain fluctuations need to influence the light source within the cable in a measurable way to provide useful data. When light photons are scattered randomly after contacting particles within a fiber, this is known as Rayleigh scattering. This principle has proven useful with various types of fiber testing techniques such as OTDR fiber testing because the volume, wavelength, and location of light backscattered to the detector can determine the magnitude and position of attenuation events within an optical fiber. In a similar way, Raman scattering produces temperature-induced changes in photons scattered back to the source in the Stokes band. By measuring the difference between the intensity of backscattered light in the Stokes and anti-Stokes bands, the temperature can be accurately determined at any given location along the fiber. Brillouin scattering is a similar phenomenon where the backscattered light wavelength is influenced by the external temperature and acoustic stimulation in a predictable way. This data, when coupled with background knowledge of temperature at the same point, can be used to accurately determine the strain experienced by the fiber and analyzed to determine what areas, zones, of the fiber are impacted. Raman and Brillouin scattering are effectively used in distributed fiber sensing, DFS. Raman scattering is used for distributed temperature sensing, DTS, and Brillouin scattering is used for distributed temperature and strain sensing, DTSS. These measurements are not influenced by the optical loss of the fiber, so they can be used to monitor the temperature and strain accurately over tens of kilometers. In this context, distributed simply refers to fiber sensing technology that can measure continuously throughout the complete length of the fiber, or distributed fiber optic sensor. Essentially, the fiber itself is the sensor. Since these fiber sensing methods are completely intrinsic, standard telecommunications fiber can be used as the medium if the temperature is expected to remain below 100 C, 212 F, and the fiber is not subjected to excessive chemical or mechanical disruption. Before fiber optics had emerged on the scene as a telecommunications method in the 1970s, the obvious potential of fiber for sensing applications was already being realized. The photonic sensor, an extrinsic fiber sensor used for non-contact vibration measurements, was patented in 1967. By the mid-1980s, fiber optic gyroscope principles had been established. By tracking the phase shift of the laser light source contained within the fiber, precise rotational data could be obtained. Here are a few applications which can be addressed with fiber sensing interrogators. Optical network sensing: protect, inspect, or monitor optical fiber networks. Infrastructure monitoring sensing: a fiber can be used to conduct infrastructure monitoring by using the fiber as a probing device. In this use case, one can deploy a fiber along critical infrastructure such as a bridge, pipeline, secure aperture, or dam wall to set off an alarm if the fiber demonstrates sudden strain, movement, or the temperature of the fiber puts the infrastructure at risk of damage or failure. This can be used to secure openings such as doors or manhole covers to generate an alarm if the opening is breached. Several infrastructure monitoring applications are available with Viavi fiber sensing interrogators. Detection of ground movement along a pipeline. Detection of mechanical deformation of the pipeline. Detection and location of any leakage along a pipeline, dike, dam, etc. Detection and location of any critical point in a telecom optical network. Detection and location of any hot spot along a power cable. The Viavi fiber sensing portfolio includes DTS, distributed temperature sensing, based on Raman OTDR technology. DTSS, distributed temperature and strain sensing, based on Brillouin OTDR technology. Using a portable, such as the Viavi TBERD/MTS 8000 platform with a DTS or DTSS module, an inspector can go out into the field and conduct field measurements on fibers. Alternatively, Using ONMC and a rack-mounted OTU, optical test unit, with a DTS or a DTSS module, fibers can be monitored using periodic traces that are set to alarm if there is a change from the beginning reference trace. Below is an example of the Viavi DTSS. Viavi DTSS interrogator is Brillouin OTDR, BOTDR. A short pulse of light is launched into the fiber used as a fiber optic sensor. The forward propagating light generates Brillouin backscattered light at two distinct wavelengths, from all points along the fiber. The wavelengths of the Brillouin backscattered light are different to that of the forward incident light and are named Stokes and anti-Stokes. The difference of Stokes and anti-Stokes Brillouin level and frequency is an image of temperature and strain along the fiber. Fiber monitoring provides an immediate alarm when a change is detected. It can also provide a geolocated map pinpoint for the location of the event detected on the fiber. This allows the organization to dispatch to inspect the fiber or to fix to the right location every time and eliminate the long span of time that would be required for finding a problem along a fiber. Learn more about fiber testing. Customers will report a service outage caused by a fiber break, but often when there is a break, the cable has been strained permanently on either side of the break or damage event. Take the example of a backhoe digging up a cable. The cable was pulled, tugged, and strained. Strain inspection will allow a technician to determine exactly which section of the cables need replacement and allow the cable owner to hold the party responsible for the damage accountable with DTSS fiber optic sensing evidence. The same is true for damage caused by inclement weather and debris such as tree branches falling on aerial cables. The most common but difficult to diagnose issue in the fiber of a network occurs when excessive strain is placed on the fiber. This permanently elongates the fiber, weakening it and potentially changing its light transmission properties. Below is an image of a strain test that shows 3 strain peaks using DTSS. All 3 areas of this fiber are compromised, but a classic Rayleigh OTDR will not reveal this problem. These peaks indicate this fiber needs replacement. Given the wide range of benefits already realized through fiber optic sensing in multiple industries, it is safe to assume the efficacy and cost-effectiveness of existing products will continue to improve just as new applications are developed. FOSA has explored many of these possibilities in depth, including the use of fiber sensing in smart cities, integration of the Internet of Things, IoT, and innovative new fiber variations designed specifically for more challenging environments.